Well, good morning, ladies and gentlemen. My name is Uwe Franke from Daimler Research and Development, and it's my pleasure to chair this session on environment perception. We will have 4 papers. The first paper will be given by Maximilian Muffert, a colleague of mine, and he's going to answer the question whether it's safe to enter the roundabout.
Thank you very much, Mr. Franke. Dear ladies and gentlemen, welcome to the first talk in the session. In my talk, I will present you a start and stop assistance system for cars or for a car who wants to enter roundabouts. Well, I think everyone here knows that the most accidents occur at normal intersections. And one strategy is to build roundabouts to reduce the number of accidents or avoid accidents. But please take a look to the yellow van. To the yellow van or to other cars, it's possible that the drivers overlook cars from the left side or in front of the cars, and so dangerous situations could occur. And that's the reason, or that's our motivation, why we want to help the drivers in such dangerous situations. Here on this first slide, I would present the main components of our procedure. And of course, the talk has the same structure. First, I will present our stereo camera setup. Then, with the help of the rectified image sequences, object detection is carried out. And then, for each object, time to collision is estimated. And this time is an indicator if an entrance in the roundabout is allowed or not. First, I would like to show you a video made by a normal or standard camera system, which is aligned in driving direction and has a limited field of view. And you recognize that this configuration is not sufficient for our task because the cars are detected or recorded too late. And so we have to change our setup. And due to this, we mounted a spherical 360-degree camera on our research car and recorded about 50 roundabouts. And for better image understanding, the middle of the image is driving direction. And during this test drive, many people looked at us. And here a very interested man came to us and he wanted to know what we are doing there. And I think you asked the same. And I mentioned that the middle of the image is driving direction, and we defined this driving direction as the horizontal viewing direction 0. And now we marked all relevant cars which enter the roundabout and estimated the horizontal viewing direction. And here you can see our results. About 95% of all relevant objects occurred between -90 and -20 degree, and this area should be observed for this task, for our task to observe oncoming cars on roundabouts. And of course, this is independent from the kind of sensor, but in our case, we use a stereo camera setup because high-quality cameras became cheaper and cheaper. They are very flexible, and we have very efficient methods of stereo vision. Mr. Gavila talked about very efficient methods in the first talk. And yeah, here you can see our setup. We assume right lane driving, so our system looks to the left side. We have 80-degree lenses, and our baseline is 35 centimeters. And now, in contrast to the first video, you see the cars are recognized or recorded early. Now in the next step, we estimate dense disparity images with the help of the rectified image sequences. And here we use the very efficient method of the semi-global matching. It was introduced by Heiko Hirschmüller 2005, and 2009 real-time application was published. Here you can see the red dots stands for near objects and green stands for objects or disparity values which are far away. And now for better object detection and a better scene understanding, we use or we generate our Stixel world. This Stixel world or this procedure was introduced by David Pfeiffer 2010 and 2011, and the name comes from stick, from stick and pixel, so we get Stixels. And a Stixel is a vertical rectangle with a defined width and a variable height. And here you can see a Stixel in the same color encoding. Red Stixels are Stixels which are near to our ego position, and green Stixels are far away. The advantage of this procedure is the enormous data reduction. We have only 600 Stixels in contrast to about 600,000 pixel values. And you see the car is described by a set of Stixels. Another advantage of this representation is that we could track the Stixel over time with the help of Kalman filters, so we get motion information too, and here it's represented by the arrows. In the next step, we group the Stixels to clusters or to objects, because for following time to collision estimation, we are interested to get the collision time for the objects and not for 600 Stixels. And here we use the idea of the so-called LDB scan, and we get for each object, in this case we have two objects, the mean position and mean velocity. On this slide I would show you some results. At the bottom, at the top you see the results of our Stixel generation, and at the bottom our cluster results from the bird view. You see here the rectangle is the ego position, the red dots are Stixels with a velocity greater than 0, and the border points of the rectangle describe the border points of our clusters. Now you can see we have 3 objects in the scene, 3 clusters. Now only 2. And now you can see the car in front of us is described by this cluster, and the car on the left side is described by this cluster. Now, after the object detection and recognition, we want to estimate the possible collision time between an oncoming car A and a possible collision point P. And the possible collision point is in front of our ego vehicle. And of course, both cars want to enter the roundabout. And the major question is it allowed to enter the roundabout, or is it not allowed to enter the roundabout? And here, the challenge is we don't know the way which object A will drive. And here are many possible driving sets. You see the car could take the first exit or could drive to this point, and this is very dangerous point, because it's very hard to decide if the car will leave the roundabout or will pass a possible collision point. And in our case, we assume that all objects pass the ego vehicle and will pass a possible collision point. And so we could describe the expected trajectory as a circular arc. This is a very defensive method or assumption, but from the view of a driving assistance system, a safe assumption. Now we assume that we have tracked the car over a few time steps, and now with the tracked points and the possible collision point P, we make a circle fit. And after the circle fit, we could calculate the expected driving path S, and with the length of the path S and the current velocity of the car, we could estimate a possible or virtual collision time between our oncoming car and the possible collision point P. Now, the last block, on the last block of my talk, I will present results. Here you can see at the top the original image sequence overlaid with the stick cells, and above, at the bottom, sorry, the results. We see the ego vehicle again, possible collision points. The clustering results. This cluster is represented by this object. We have a current. You see the current circle fit, and the TTC is about 4 seconds. Now the traffic light switched to red because the time was under 2.5 seconds, and this time was, we estimate this time from physical and geometrical assumptions. Perhaps I would show the video again. And the purple points represent the driven trajectory of our object here. At the end, we evaluate our procedure with test persons. In this case, we use our students, our bachelor and master students, and they look to our video sequences, and they told us if they would enter the roundabout or not, and so we get the time windows where they would enter the roundabout or not. And here are our results. The first line represents the behavior of our algorithm. Of course, red stands for it's not allowed to enter the roundabout, green for it's possible, and the next 10 lines are the behavior of our test persons. This is an example of our evaluation for a 90-second sequence. And in these scenes, you see that our algorithm corresponds very well with the behavior of our test persons. And here I have shown a small video too. You see the oncoming car. That's not an easy scene because in front of us is the traffic sign, but we get the objects here. And now it's red again. Now we have some scenes where the algorithm doesn't correspond with the behavior of our test persons. You can see some red phases in contrast to the green phases. And that's the reason why the test person recognized vehicles who pass or who takes exits. And a very interesting scene is the beginning scene, because you see the behavior of the test persons is very different. They're very different, and you see a very a defensive driver, for example, driver F. The driver said it's not possible to enter the roundabout, and here a very aggressive driver B would enter the roundabout 3 times. And now you see the results of our algorithm. Here the most test persons recognize that the car will leave the roundabout. Here's only now a small window to enter. It's red again. And now the driver B would enter, and I think this is a very dangerous situation, and our algorithm says, no, please stop. And I think from the view of autonomous driving assistance system, it's better to stop there. And yeah, that's the last slide. At the end, a short conclusion. I presented a new stereo camera system for the observation of roundabouts. We use efficient methods of stereo vision for the object detection and for the tracking. We estimate possible collision times between oncoming cars and possible collision points, and we evaluate our procedure with the help of test persons or of our students. So thank you very much.
Thank you, Max. We have time for 2 questions. Please here. Is that the microphone? It's coming.
So yesterday, Chris mentioned in this kind of emerging situation, so the host car can do something to signal the other cars. So do you consider, or in this kind of situation, if you move a little bit to signal other car, is there some influence to the behavior of other cars, and how does it to change your system?
Yeah, it would be better to analyze the driving behavior, and when we know the driving behavior of the cars, perhaps it's possible to enter the roundabout when a car will leave the roundabout. But we started with the observation of roundabouts, and I think it's better to assume that all cars will pass us, and so this is safer, I think.
Yeah, I think for Spanish roundabouts we have to adapt a little bit. Other questions? I can't see any. Then thanks, Max, again.
Okay.
And we proceed to the next paper. Next paper will be by Thomas Kwotak from University of West Bohemia in Pilsen, Czechoslovakia. And he will talk about the condition assessment of drivers based on acceleration signals.
Okay, welcome to my presentation. My name is Tomáš Kwotak and I'm from University of West Bohemia in Czech Republic. And the topic of my presentation is analysis of acceleration of a vehicle for assessing the condition of the driver. Firstly, I will be shortly speaking about driver. Then I will describe our method of work. The next point is the measurement, and then acquired data, and the final part of my presentation is the conclusion. It's shortly to structure. Due to the mental character of main factors of driver's behavior, it is not possible to make direct measurement. Many studies and approaches use specific expression in the driver behavior as a metric for an opinion about current condition. It is necessary to choose a specific indicator that can be evaluated during the drive. It's an increasing burden of drivers' an increasing burden reduces the driver's ability to interact with the environment. Typical indicators are increased variation of speed, reduction of higher value of deceleration, and speed reduction. The increase of the driver's task load can cause changes in the lateral steering too. The aim of our research is to verify the possibilities of detecting temporal variable factors in the driver's behavior by analyzing key characteristics of lateral and longitudinal acceleration of the vehicle. We work on the assumption that changes in the driver's condition should be evident in his driving style. Measurement. Measurement took place on an enclosed area where cones marked a track. Cones are this blue point. This track was built so that it contains two different radiuses, one bigger and one smaller, and one stop line. The stop line was placed so that so as to obtain the combination of the effects from a lateral acceleration when driving around the bend and from braking at the stop line. The participants were instructed how to drive this designated road. They had to drive in his normal driving style 3 times around. And it was necessary to stop in every lap at the stop line. Two groups of drivers participated. The first group was students of a driving school who drove around the track under the supervision of under the supervision of an instructor in the car of the driving school. These students constituted a model of beginners without driving habits. The second group was ordinary drivers. They had more experience of driving control. To acquire data. The acquired data are shown in form. Acquired data are shown in form of 3 graphs, which is always related to one driver. In the first graph first graph shows longitudinal and lateral acceleration over time. This blue curve is the lateral acceleration, and this red curve is the longitudinal acceleration. The second graph is a pie chart where the lateral and longitudinal acceleration were plotted in form of scatter chart. In the x-axis are recorded lateral acceleration, and in the y-axis are shown acceleration in the longitudinal direction. And the sales graph shows spectrum of vector of acceleration. Vector of acceleration is a vectorial sum of lateral and longitudinal acceleration. It is a graphical representation of interval frequency distribution of a vector of acceleration. On this slide, you can see records of 2 drivers. The first was an ordinary driver, and the second was a student of the driving school. a few findings are evident. For all drivers there was obvious difference between the first, second, and third lap, because none of the driver had a chance to drive around the truck beforehand. When we comparing this lateral acceleration for the students, for this student from the driving school, is evident this correction of the wheel after entering in every drive. This is only one thing. On this slide, you can see data from one of the drivers. These drivers had to drive in the first circuit in his normal driving style. This is this. And before the second lap, he was asked to drive slightly faster. When comparing the two graphs, a noticeable increase of lateral acceleration, this is into bands, can be seen. Regarding the shape of the lateral acceleration, for example, this second band, there are no significant differences. Only in the first lap of the second run is a correction of the wheel when entering the first band. When comparing the longitudinal acceleration, it is evident that the increase of maximum values, this is this 3 for braking before the stop line, is only slight. This slide shows data from one of the drivers. These drivers was asked before the second circuit to drive around while making a phone call. Calling is one of typical additional activities during driving, I think. But in many countries it's forbidden. On this slide you can see two graphs. This is acceleration, lateral and longitudinal over time, and the spectrum of acceleration backward. The idea was to give the driver an activity which would employ part of his attention. This restriction of attention ought to be reflected in the manner of driving, which was confirmed by the measured data. At first glance, the course of the second run should be appears to be a little unsettled. This is this difference, for example. During lateral acceleration, the corrections of the wheel are evident in every band, like for the students of the driving school. The maximum values for lateral acceleration into bands generally declined. That's confirmed as is often described in the literature. The driver's efforts during additional activity to modify driving parameters to decrease driving demands. When we comparing the lateral acceleration, longitudinal, we can see this change of maximum values from longitudinal acceleration. This appeared for only a few students of the driving school in the first part of our experiment. The difference is also apparent during acceleration when starting the vehicle. This is indicated with this green mark. Okay, and now conclusion. In the driver vehicle environment system, we ensured the repeatability of environmental element. all drivers drew around the same track. For students of the driving school, even the same vehicle was used. Thus, differences in measured data were caused solely by driver. Also, these factors were recorded on a number of drivers that cannot be considered a sufficient statistical sample. But I think it suggests the direction that needs to be further analyzed. In the further research, we will focus on braking with and braking without additional activities that loads drivers' attention. Thank you for your attention.
Thank you, Thomas. Interesting to see how bad we students drive, and a couple of years later they're so much better again. Other questions? Let me ask a question. You did your tests on a closed area.
Only.
What do you think if you go downtown in public traffic and the actions or reactions of the driver will depend on the other traffic? Have you any ideas how to cope with that?
I tried it with a few students of the driving school, but the environmental factor is there another, and the data there are big differences in the acquired data, and I think I prepare it for a classification with an artificial neural network. It is in this first phase is better use this condition, this same condition for all of drivers. And what you say, this environmental factor make difference. It should be better in further work.
Other questions? Everybody seems to be hungry. Okay, then we finish this talk. Thank you very much, Thomas, again. We come now to the third talk given by Michael Himmelsbach from the University of the Armed Forces in Munich, tracking and classification of arbitrary objects with bottom-up and top-down detection.
So thank you, Mr. Franke, for the introduction. And ladies and gentlemen, I welcome you to my talk. And this talk is going to be about tracking and classification of arbitrary objects with bottom-up, top-down detection. And one of the points we want to stress in this talk is that it is especially useful to integrate top-down knowledge into this tracking architecture. And this will be one of the main points of this talk, but then we will also cover classification of tracked objects. Yes, on this first slide, you all already see the main sensor used in this work is Velodyne, and you know it already from the talk of Chris Urmson in the keynote yesterday. So let me just say some introductory words about tracking in 3D point clouds. The common approach to tracking in 3D point clouds involves a decomposition of the problem into components for segmentation, data association, tracking, and finally classification. And it's not only our experience, but also that of colleagues from Stanford. Alex Teichmann published a work on the IV, in the ICRA last year, that most errors in tracking and classification are due to failures in the first component of this architecture, which is segmentation, and then with wrong segmentation you probably get problems with data association as well. So what kinds of segmentation failures can we expect? Well, segmentation first means just a partitioning of the 3D point cloud into disjoint subsets. And then the typical failures are first under-segmentation, where the partition just contains too few sets. That is, objects are not properly separated from each other. We've got too few objects. And then there's over-segmentation, just the opposite. The partition contains too many sets, so too many objects, which involves that single objects are splitted into multiple components. And this actually happens mostly because segmentation algorithms involve some spatial constant that governs the grouping or splitting of segments. And if you have a look at these two pictures, you see a situation where one of these segmentation failures is probably to occur. You see a pedestrian approaching static structure very closely. And if you have a look at the bottom picture, you see that an under-segmentation of the pedestrian and the static structure is likely to happen. So we didn't separate the static structure from the pedestrian. So how can we avoid the segmentation failures? Well, first of all, we could just concentrate on parts of the scene where segmentation is easy. And I think this was mentioned by Chris Urmson yesterday also, where they localized themselves and then had the spectrum map containing road geometry, and then they were just concentrated on objects on the road. We could try to avoid segmentation at all, and there's an interesting work done by Petrovskaya from Stanford University that uses a particle filter framework. And in this work, segmentation is only needed to initialize new tracks. But still, there's a spatial constant that governs the assignment of weights to the particles. Obviously, knowing the exact geometry of all objects in the scene would be helpful, also the position. But then it turns out that it is hard to provide exact geometries for all arbitrary objects that may enter a scene. And even if we had these geometries, then finding a global match between all these geometry models in the database and the actual scene would be computationally inefficient. So, but in our approach, we thought, well, having these geometries would be nice for segmentation. So we thought about, okay, why not let us integrate information about the tracked objects we already track, from the top down to the segmentation component. So then we will have knowledge about the estimated geometry of the objects and their position. And this is indicated in this architectural overview, where you can see this blue arrow pointing down from the tracking component to the segmentation component. So I'll shortly cover the bottom-up pass, where we don't have top-down knowledge about tracked objects, but still want to segment the point cloud. So first we separate ground from non-ground points. Then, as is usually done, we just find connected components in a regular 2D grid, where we have mapped all non-ground points to. And this is the delicate step, because doing these connected components involves choosing a size of the kernel. And this kernel size actually, together with the resolution of the grid, defines the minimum distance at which objects can still be separated from each other. And just as a detail, as this first step involves segmentation in 2D, we then check these components to see if they need treatment in 3D, as is, for example, the case for a vehicle that is parking beneath a tree or passing beneath a tree. You can see the situation in these pictures on the top. So as a final step, to get a more compact representation of the objects, we then fit oriented 3D bounding boxes to these components, which involves removing the outliers from the point clouds and then issuing a Renczak-style fit to the dominant line in the point cloud, which gives us the orientation of the object. And these are then our bottom-up object detections, which are then fed to the tracking algorithm. So now we want to use knowledge about the tracked object and where we expect them to be and how we expect them to look like. So to get this information, we need some object tracking, and I don't want to go into details about tracking. It's just an ordinary unscented Kalman filtering-based interacting multiple model estimator, where we mix standard models for the motion of objects. So now to make use of this information, we need some representation we can use for segmentation out of these tracked objects, and so we estimate as part of the whole system state of a track the 2D pose and size of tracked objects. And together with the associated covariance of this estimate, we can then predict the states using information about our ego motion, and this prediction then gives us a hint about how the object might look like in the current scene. And we can also define a bounding box out of these expected objects, just as for the bottom-up measurements. But when constructing these expected object geometries, we need to take into account their uncertainties, and we do this by accounting for the uncertainty by a factor of n sigma, which controls how much of the uncertainty in geometry is accounted for. You can see this in the bottom picture, where the green boxes denote the estimated states of the tracks, and the blue boxes the expected appearance. In this picture, n sigma is equal to. So now we've got information about the expected objects, and now we want to integrate them to refine our bottom-up segmentation. So again, it's these failure modes, two failure modes, over segmentation, under segmentation. They are treated separately. So let's first handle over segmentation. Again, in the picture on the top, there's an example showing how over segmentation of a passenger car might look like. So these gray level points usually really correspond to one passenger car. So, and we detect this over segmentation situation by looking at two bounding boxes of detected objects, like these magenta colored ones, are contained in the box of an expected object. And we compute this containment using Boolean polygon operations on the bounding boxes. And you might ask if requiring containment is too strict, but it turns out that it is okay to do so because by accounting for the uncertainty, the expected object boxes are usually larger than the measured ones. So now we detected over segmentation. We need to handle it now, and this is in the case of over segmentation simply done by combining the connected components that are contained in an expected objects box into a new one, discarding the one resulting from bottom up detection that represented an over segmentation, and getting us again a bounding box representation of the new component. So after having handled over segmentation, we now have to handle under segmentation and detect it first, of course. Again, the top picture shows a situation of under segmentation denoted by this red bounding box, where there's a passenger car driving by closely to this static structure, and there's some sensor noise you see, so this makes it hard to separate them too. We can detect this situation of under segmentation now by looking for an expected object's bounding box that is contained by a bounding box of an object detected by the bottom-up pass. So it turns out that it is important to do this after the handling of over-segmentation, because the latter might result in under-segmentation itself. So now we detected the situation, we still need to handle it. And this is now done by iteratively refining the segmentation of one of these under-segmented components, say CI, using decreasing kernel sizes that are smaller than the kernel used in bottom-up detection as 0, and using a smaller kernel in each iteration. And it turns out that this is a very fast local operation, because we only need to consider the cells that made up the under-segmented component CI. So for each new kernel size, we now get new connected components, and we stop if these new connected components contain a component whose box is contained in the expected objects box. So now we really took the information about the appearance and geometry of a tracked object and to refine the bottom-up segmentation. And then, of course, we need to replace the under-segmented component CI with the new components. So this slide now shows some results of using the top-down information, and it also shows the benefits of doing so. As you remember, the situation of the pedestrian approaching the static structure, you now see that by integrating the top-down knowledge about the tracked object, the tracked pedestrian, we are now able to separate it from the static structure. And then the second row shows further situations of where under-segmentation has been detected and handled. Again, you now see the pedestrian, but it also some situations where, again, a vehicle is approaching static structure, a parked vehicle is very, very close to static structure, and some situations where the sensor noise makes it hard to discern vehicles, even if they are driving the street. The bottom row now shows situations where over-segmentation has been detected and handled, and this is all cars, and situations like these typically happen for objects far away to the sensor, or if the objects have a bad angle, bad orientation to the sensor. But still we see that integrating the top-down knowledge is beneficial. So this slide now shows some examples of results for the object tracking using the system. I don't want to explain all the choices of the parameters involved, but just let you know that these choices actually allow execution of tracking and classification at the rate of the sensor in 10 Hertz. Unfortunately, doing a quantitative analysis is hard for such tracking algorithms because well, you can't get ground truth data for all these objects. They need to be equipped with some kind of inertial or global positioning system. But still you see in the picture that simultaneous tracking of multiple objects is possible, even at this challenging inner city crossing scene. And you also see that the pedestrians could be tracked nicely. So now we also want to do track classification. And most of all, we're interested in the classes pedestrian, bicyclist, motorbike, passenger, car, and truck. And we want to use different feature types to classify these objects. These tracks, I want to say, sorry, it's really not object classification, which would mean we would just have a snapshot of the object appearance from one instance of time. But we really want to classify tracks. That is, we want to include information about their motion that we got by observing them over multiple time steps. So still there are some appearance-based features involved. For simple ones, it's just the length with height of the object as well as the size of the point cloud that was last associated to an object. You can see this last associated point cloud in this picture on the bottom here. It's color-coded by height. Then, of course, we know something about the object's motion from tracking, and assuming that our dynamic models provide us the information, which they do in our case, we include 8 motion-based features, namely the extremes of velocities, positional velocities, and accelerations, but also velocities and accelerations in the orientation of the object. But as our robot is equipped with an inertial system, or if we would do like a self-localization algorithm, we are still able to generate a trajectory of the tracked objects by integrating our ego motion if the robot is moving. So now a trajectory just means the last m estimated 2D poses in an inertial system now. And the picture also shows an example of such a trajectory with 5 poses. From this trajectory, we can compute further features. We are using the central difference function of the trajectory that just relates every pose of the trajectory to the mean pose of the trajectory. And also the Fourier transform of the central difference function is used as a feature, giving us a total of 12 plus 2 times m features for each tracked object. So we hand-labeled approximately 300 tracked objects, and the distributions of these 300 objects among the classes is shown in this picture here, top left picture. Then we split the set into two equal-sized, randomly split the set into two equally sized sets, one for training, one for validation. And actually the picture on the right shows the distribution of the validation set. And I was sorry, this is the distribution of the training set, not the distribution of all the labeled tracks. So we then used a quite simple naive Bayes classifier with Gaussian kernel density estimates of the class-specific feature distributions. And this turned out to be to already produce nice results. The resulting classifier would classify 93% of all tracks correctly in cross-validation. Most of the problems or the false classifications occurred between vans and passenger cars, as you can see in this confusion matrix here. So this will be the last slide of my talk, showing an impression of tracking and classification combined now. So in this video, the color of an object's box denotes its class. So yellow will be like truck, and green will be a passenger car. And this video finishes my talk, and I'm open to your questions now. Thank you.
Thank you. Other questions?
Thank you for this great presentation. I have one question. It is about the sensitivity to initial conditions. It seems to me that if the initial condition, the initial bottom-up segmentation, is already over or under segmented, the whole chain might collapse. So can you comment a little bit on this?
My opinion is that you won't find a single constant for which you arrive at a pure bottom-up segmentation without one of these segmentation failures. And I don't think that this whole chain will collapse for any choice, because you can't do any bad or good choice.
No, what I mean is, you showed this example of the pedestrian approaching the static structure. So that relies on the fact that you have correctly segmented the pedestrian before he was approaching the structure. Now,
okay, you're right, yes. This is one of the topics we want to cover in future work. Of course, for initializing tracks, we still require pure bottom-up results of segmentation.
Which would seem to me would work in most cases. I mean, don't get me wrong, I think this will work in 98% of the cases. So
yes, of course it is hard if the track starts in situation, if you want to track this pedestrian and he starts from a static structure close to static, then yes.
Okay, thank you.
There's another question here in front.
I didn't really be aware of the time that it takes to make the classification online. Did you care for that?
Yes.
You have to
I don't have timing results. I just know that the algorithm tracking and classification can be done at sensor rate, so at 10 Hertz. But you know, this naive Bayes classifiers are known for the simplicity, also for the computational simplicity. So because all these different dimensions of the feature space are treated independently. So these are really fast to classify.
As you want to use it online, you have not much time. I mean, tens of seconds or something like that.
So, sorry, I didn't get it.
If you want to classify, use that scheme for online tracking,
yeah?
Then you have a tenth of a second or sometimes, depends on the density of the traffic. So I wonder about this segmentation scheme that you have, that you can do any of that in real time, under this kind of constraints.
Okay. I think I got your point. The algorithm might take a little bit longer if there is a really large object that has to be refined iteratively. So this would increase the computational load. But it did not encounter in our tests that said the algorithm would not run at sensor rate. And the density of the point cloud is static. It's always 100,000 points a second or so.
There, third question. It's hard to see for me from above here. No, doesn't seem so. Thank you very much again.
You're welcome.
Let's proceed to the last talk, which is given by Wojciech Popescu from Technical University of Cluj-Napoca. And she's going to talk about on-road position estimation.
Hello, my name is Wojciech Popescu. I'm with the Technical University of Cluj-Napoca in the image pattern and image processing and pattern recognition group. I'm a PhD student, and work that I'm going to present today has been done in collaboration with my colleague Radu Dănescu and under the supervision of our professor, Professor Sergiu Nedevski. The title of the work is On-Road Position Estimation by Probabilistic Integration of Visual Cues. The outline of my talk: I will present the context of the work, the goals and motivation, the clear objective, the proposed method, results and conclusion, and future work. The context is the theme of localization, which has gained an increasing awareness from the research community in intelligent vehicle transportation domain. So the most classical approach for localization is based on a global navigation satellite system. And this solution has been enhanced by addition of vehicle onboard sensors, such as inertial navigation system, odometers, vision, and others. Also, an important aspect added for localization is the use of digital maps that have been developed and extended such they become more complex and contain detailed environment information. Also, inter-vehicle communication can aid in localization. An important aspect is determining the lane level position, considering that we are dealing with an urban structured environment. And this is provides immediate application for any driving assistance system. An important visual cue for this kind of positioning, for lane level positioning, is the lane boundary classification. There exist in the literature frequency-based analysis and pattern-based analysis. Most of them use Fourier transform. Our goal are, in this paper, to identify the class of boundaries for the current lane, which are important visual cues for lane level positioning, and to find the lateral position of the ego vehicle on a multi-lane segment. We are under the assumption that we are using an extended digital map which contains more than just the GPS measurements of the position, but also the number of lanes, the type of the limiters, the type of painted arrows. What is the motivation? Having this information can help navigation system, for example, lane selection prior to intersection. It's a step closer to accurate global localization, enhanced environment representation, for example, using vision and digital map information, also enhanced environment understanding, and collision avoidance system can benefit from the lane level positioning system. The clear objective that we have settled and obtained through this paper are lane boundary classification, which is done based on the frequency analysis of the gray level profile of these boundaries under the assumption that the current lane is already detected by a lane track system. The second objective is position estimation based on a Bayesian network that performs by frame reasoning based on the visual evidence and provide probability distribution over the set of hypotheses, which are the number of lanes of the current road. And the final step is to track in time the time instance result to obtain more stable results and to consider the dynamic nature of the problem. So the first objective, lane boundary classification, is composed of the following 4 steps: the feature extraction, the temporal integration and filtering, the lane boundary classification, and detection of double delimiters. The first step is to extract from the image, the gray level image, the features that we will use in the classification. We are interested in the grayscale values along the lane delimiter and their relationship with the immediate asphalt region. Therefore, we generate in 3D space a set of equally spaced lines covering a distance of 20 meters. We can see these lines in the image in the bottom right, where with white we see the points covering the delimiter region and the gray points covering the asphalt region. So we generate these 2 search regions. The first one, with white, the most likely to cover the painted marking, and the second one most likely to cover the asphalt inside the region. We then average this grayscale and for each point, and we obtain 2 averages: the average value of the marking area for left side and right side respectively. Then we obtain the average value of the asphalt area inside the lane marking. And the next step is to compare this average. If the average of the marking area is greater than the average of the asphalt area with a low fixed threshold, then we set a value of 1 in a binary signal. Otherwise, it will be a value of 0. So this is the obtained binary signal. So for now, we have the lane boundary classification up to the point that we have a binary signal that expresses the relationship between the asphalt region and the marking regions in interval of 0 and 1. We have this at each time instance. Of course, each time instance is not should be filtered because error can occur, such as a limited field of view or occlusion of the lane marking. So we integrate this binary signal. We use an offset computed from the velocity and the time interval, and we average out the results. That is the result of the current frame with the result of the previous frames. We expand the distance interval such that we will cover a distance of 30 meters. We obtain so a longer, more stable binary signal that describes better the type of markings. This is the binary signal obtained. And the final step is to smooth it, and we do this by adding a Gaussian kernel. So we obtain a signal composed of continuous values, the filtered binary signal. From this filtered binary signal, we extract several features used for classification. We will analyze the number of ones in the signal and the shape of the signal. So from the number of ones in the signal, we obtain the first feature, one count. That is the number of ones in the signal continuous values. We take as 1 all the values greater than 0.5. And about the shape of the signal, being a periodic signal, we use a frequency analysis. We propose in this approach to compare the signal with itself at different time intervals. So we define a period histogram in the equation at the top of the slide, in which for each candidate period t, we sum the absolute values of the signals time space with a value of t. The period histogram obtained will peak for those values corresponding to the spacing between the middle of the dark and the middle of the white intervals. So we obtain several peaks. We are interested, we will take for our classification the two ones. The first peak corresponds to half of the period of the signal, and the second peak corresponds to 3 times this value, so 1.5 period of the signal. The local maximas for the period histogram are defined as t first and t second. T first corresponding to 0.5 period of the signal, and the second one will be used for validation. For a periodic signal, the ratio between the second and the first should be approximately 3. So these are the second and third feature used in classification, the half period and the peak position ratio. We have defined the 3 features. The first one should be high for a continuous lane. The second one, the peak position ratio, should be around 3 if we are dealing with a periodic signal, which indicates an interrupted or a merged type of marking. And the half period should have a definite value. The exact rules for determining the classification are extracted using the decision tree learning system from VECA. 2 examples are illustrated. In the top, we see the test case image. In the left, the filtered binary signal, the period histogram, and the first and second local maxima of P. I would like to draw the attention that for the local maxima, we see that the second point for the left side delimiter, the second point is has the position 3 times the value of the first one. This indicates clearly that we are dealing with a periodic signal, which is the case because the left delimiter is interrupted. The right side delimiter does not obey this rule, so it is not the case that we are dealing with a periodic signal, which is actually correct because the signal is continuous. And the second example, the similar observation. This time the lane boundaries are merged. Lane boundaries, so shorter interrupted. And we can observe also the peak ratio feature. This, the rightmost image. Now we have classified until now the single delimiters. Well, for the detection of double delimiters, we also analyze the lateral shape. We generate wider search areas such that the double markings can be covered. We are interested only in those regions in which single markings have been detected, because only there can appear the possibility of having double lines. We classify the pixels based on their intensity as marking. If the intensity is closer to the intensity of already marked, already classified as marking region, or non-marking if the pixels have an intensity closer to pixel classified as asphalt region. We then count the transition between the marking and the non-marking pixel sequences. We can see in the image in the right that for single lane delimiters we have 2 transitions, whereas for double lane delimiters we have 4 transitions. We average this transition for all the points, and if we obtain an average value greater than 3, we classify the delimiter as being a double delimiter. We have experimented our proposed method through a test case scenario of 8 kilometers in the center of our hometown, Cluj-Napoca. It covers a long distance within the center of the city in which all these type of delimiters have been encountered, each with different frequencies. And I would like to mention that also the quality of the marking varies a lot. As we can be seen in the image, the following line is kind of worn out, which affects also the classification. In the right, we see the table with the experimental results. We can see that the true positive rate is high, not as high as we would have expected. This is major, especially because of the worn out markings. But the positive thing is that the false positive rate is very low. So this is a very, we can trust this algorithm. It's a very reliable approach. I will leave it just a little longer so you can see also double line on the left and or worn out marking on the right, which is more difficult to classify. It is sometimes classified as interrupted, sometimes as merged. Okay, and it should appear on the left side also double interrupted for a very short period. Any minute now. Okay, that was it. We moved then on to our second objective, which was position estimation. Estimating the EGO vehicle's lane number on a multi-lane road segment. We do this considering that we have an extended digital map from which you know the prior structure of the road that we are traveling on. And we use as evidence the visual measurements, the type of lane boundary classification. These are used for data association with the lane marking from our extended digital map. We use also additional information, the type of painted arrows useful for case in which we are approaching an intersection, and also additional useful information comes from the other vehicles in the environment. If we have vehicles traveling on our left side, on our right side, and we know that they are going or coming, provides useful clues about our position on the road. We use a probabilistic approach in order to deal with the uncertainty and noise specific to sensorial information, and the method proposed is a Bayesian network because of its advantages. It provides human-like reasoning, which we are interested in this case. It deals well with incomplete and uncertain data, and the instantaneous beliefs provided will be filtered over time such that we get a more stable estimation. The main idea of the reasoning mechanism is that the proposed network encodes the relationship between the traffic elements, that is the EGO vehicle, the other vehicles, and the lane markings. And the visual measurements are used as evidence in order to infer the state of the EGO vehicle. The structure of the network is the one illustrated in the figure. The first layer illustrates the nodes that are observable. The type of left boundary type, the type of right boundary type, the type of painted arrows, and information about other vehicles. The second layer is a hidden layer. We use it as an intermediate level, such that the conditional probability table of the hidden node, EGO lane node, will be reduced. The EGO lane node has the states, the number of lanes of the segment we are traveling on, and by the evidence provided in the network, the posterior probability distribution of this node indicates the estimated position on the lane. I would like to mention also the parameter. The parameters are learned for every segment in part. So they are learned using the information from the extended digital map as data set for in the maximum likelihood estimation, because we are dealing with complete data case. At each time instance, the evidence from the visual perception system is used, and a posterior probability distribution is obtained. So for each lane from 1 to L max representing the number of lanes of the segment, we obtain a weight for each of the lanes. this is the measurement that will be passed on to the particle filter. Again, we cannot rely only on a single frame results, so a method to integrate this in time was required. We did this using a particle filter. So at each instance state, the lane number probability density is approximated by a set of n weighted particles. Each particle will retain a hypothesis and a weight encoding the strength of this hypothesis. The particle filter has the three main phases: resample, in which the past weights are used to generate new population by making n random selection and using the weight of the particles as measure of the probability of it being selected. A small set of particles will be randomly distributed among the hypotheses. The second step of diffusion alters the state of the new population of particle. Each particle will get a chance R to move to its leftmost, to its neighborhood to the left, to the right, and it has a chance of 1 minus 2R to keep its hypothesis unchanged, that is, to remain on the same lane. The measurement step is the one in which to each particle it is assigned, a new weight is assigned to each particle. And the weight comes from prior measurements obtained from the Bayesian network. Prior reasoning, not measurements. So for each particle, we will get the new weight, its corresponding new weight. We then perform a normalization, and the steps are repeated again. Finally, the probabilities of each lane hypothesis are estimated by summing the weights of the particle sustaining that hypothesis. And now a video will be showed in which we are dealing with 5 lanes, and we can see that in such a case it is hard for the system to identify exactly the lane. However, the lanes 3 and 4 have been identified as the most likely ones. Also, for a case with 6 lanes, it is hard to say exactly which one is the correct one. However, the 4th and the 5th one have been selected as most probably. This is the case in which there are more lanes for driving in direction than 3, and in such cases, the type of lane delimiters aren't clear discriminators. So additional information is useful, and we are relying on that. I would like to draw the attention upon the fact that in cases in which there are 3 lanes per driving direction, there aren't any problem for the system to identify correctly and maintain the correct localization, lane level positioning localization. So this is once again, I wanted to emphasize that for 5 lanes, the system is trying to decide between the 3rd and the 4th. The other ones have smaller probabilities. And in the case of 6 lanes, we can see that the 4th and 5th lane have the highest probability. And the final situation is in the case of a lane change. We have only 2 lanes for driving direction. It is easy for the system to identify the first one. Now the vehicle is moving to the right, but for only a short period, and comes back. And this can be seen from the graph, blue signifying the left lane and red the right lane. And we will have another lane change, which is immediately identified by the proposed approach. The conclusions are that we have proposed a lateral positioning system on a multi-lane road, And we are relying on stereo vision information for this. The testing have shown that the approach is reliable and it provides good results. And we wanted to demonstrate the utility of a stereo vision perception system in the process of localization. And further on, this is a step in improving the understanding of the ego vehicle about the surrounding environment. Future work consists in automatic identification of marking quality, because knowing if the markings are worn out or not can significantly improve the quality of the classification. As for lane level positioning, we intend to integrate a vehicle motion model. This will make it easier to identify the changes in the lane level position. This concludes my presentation. Thank you very much for your attention, and I'm open to questions.
Thank you, Wojciech. Is there a question? We have time for one last question. Yes, please.
So the accuracy of the lane positioning depends a lot on the accuracy of the classification. So the results will be a lot affected by the lighting condition. But as long as the lane changes classification are robust, so will the lane level positioning. And further on, they are aided by the detection of other vehicles, which are less influenced by the lightning condition.
So you've tried it also in the evening or in different weather conditions? Or?
No, not in rainy or so, but in normal conditions, I would say.
Thank you.
Okay, time is over. We are heading to lunch. Enjoy your lunch, and I would like to thank the speakers again. Next session is here in this auditorium at 1:50.